All right, time for another modern physics lesson. Today we're going to take a look at Einstein's most famous equation. But before we do that, we probably ought to think back about the conservation laws that we've met this year. Just to review, a conserved quantity is one that remains unchanged during physical processes. Now that sounds like a lot. Let's talk about what that means. Well, some of the quantities we've seen so far that are conserved would be momentum. That was the very first conserved quantity that we took a look at, and we said that the total momentum before the collision has to equal the total momentum after the collision, meaning P before equals P after. And we did hit and stick and hit and non-stick collisions. So this momentum quantity remains unchanged during a physical process. That physical process in this case was a crash. And then we took a look at energy conservation. We said E total before equals E total after. And for example, we had a roller coaster going down a hill. That would be our physical process, the coaster going down the hill. And we converted gravitational potential energy into kinetic energy. And it allowed us to do things like to find the speed of the roller coaster at the bottom of the hill. And then most recently, when doing the electricity unit, we took a look at the conservation of electric charge, which says that net charge cannot be created or destroyed. So we were able to, when doing problems where you touched two charged objects together and separated them, that conservation law allowed us to calculate the charge on each object. Here's the problem with today's lesson. That whole modern physics 1905 date that we discussed earlier, around that time, people started noticing some very bizarre things. And one of those things, or two of them, is that mass in certain physical processes is not a conserved quantity, and energy is also not a conserved quantity in certain processes. We'll talk in a second what those processes might be. And those are both very disturbing finds. Now, this isn't a roller coaster problem that we're talking about here. This is, in modern physics, we're dealing with the world of the atom, and the atom has some very bizarre things that happens in its world. So energy and mass not being conserved are certainly fit that bill of being bizarre. So what are some cases where energy and mass appear not to be conserved separately? Nuclear reactions. You've studied in chemistry nuclear fission, where you take a large parent atom and split it into two smaller atoms, and you get energy out. That's a physical process. Well, it turns out if you take all of the mass before the split, so take this large atom and put it on a balance and check its mass, and then you were to take the two daughter elements, the two daughter atoms, and put those on a balance and check their mass, and you would see that the two smaller atoms' mass would not add up to the bigger atom's mass. That would show that mass is not conserved. But notice it says plus energy here. That energy came from the missing mass. So when you destroyed a little bit of mass here, it turned into energy. But still, in 1905, when people were noticing this, very disturbing finding that mass before did not equal mass after. There's another physical process known as pair production, where you have a photon traveling along, minding its own business. This could be a gamma ray, X-ray. And suddenly it disappears and turns into an electron and a positron. A positron is an anti-electron. We'll be talking soon about antimatter. It's not a thing of science fiction movies. It's a real thing. Every single particle that we can think of, electrons, protons, neutrons, they all have antiparticle counterparts. And the antimatter particle of an electron is an anti-electron or a positron. So as this photon is traveling along, it can simultaneously or spontaneously disappear and turn into both an electron and a positron. Now, if you check the total mass before, let's get our red pen out here. If you check the total mass before this event happens, the event or the physical process is the photon changing into the two particles, the mass would be 0 kilograms worth of mass. And then after this event, the electron has a mass of 9.11 times 10 to the negative 31 kilograms. That's on your front page of your reference table. And the anti-electron has exactly the same mass, 9.11 times 10 to the negative 31 kilograms. So you have no mass before, and after this physical process, you have a lot of mass. Well, comparatively, you have twice the mass of an electron. So mass is not conserved, and even energy. Here you had energy before, and you might have a little kinetic energy here after, but the energy before is not equal to the energy after. And sort of the reverse of that process is something known as annihilation, where if you happen to let a particle and its antimatter friend, here we have an electron and a positron, an electron and an anti-electron, if they get too close to each other in touch, it's known as annihilation. They disappear and they turn into photons. It's really the reverse of pair production. So here we have lots of mass before, and afterward we have no mass. Here we have very little energy before, and here we have a lot of energy. So in these three cases, for example, mass conservation doesn't work in each of them, and energy conservation doesn't work in each of them. But leave it to a genius like Einstein to say, oh, even though they might be separately violated the laws, if you look at them as one law, whenever we appear to be losing mass, we're gaining energy. And whenever we appear, such as pair production, to be losing energy, we're gaining mass. So perhaps energy and mass aren't different at all. That leads us to Einstein's most famous equation, E equals mc squared. It's by far the most famous equation in the course because everybody knows this equation, but very few people know what it's actually used for. I myself prefer F net equals ma for the most useful equation in the course, but this is certainly the most famous. C here is the speed of light, and it's squared. The speed of light being the 3 times 10 to the 8th meters per second that's on your reference table. It's the speed of light in a vacuum. And this is energy measured in joules, and this is mass measured in kilograms. So this little equation here is the conversion between mass and energy. So if you destroy a certain amount of mass, if you multiply by the speed of light squared, it's going to tell you how much energy you get out. Let's take a look at how much energy you do get out. Let's pick numbers that are so easy you don't even need your calculator. Calculate the amount of energy that would be needed, that would be released if you took 1 kilogram of mass and it was completely converted into energy. Now, we don't have a method to easily do this. We don't have like an easy bake oven that you could put 1 kilogram in, press a button, and out would pop the energy. But we do have various physical processes like fission and fusion, and pair production and annihilation, where this sort of thing happens on its own. Mother Nature takes care of it, but we really can't just put 1 kilogram in some device and get it to disappear. So let's write our equation down. E, energy, equals mass times the speed of light squared. I told you we picked numbers that are incredibly easy, no calculator needed. The mass is 1 kilogram. That's a G. And the speed of light squared is 3 times 10 to the 8th meters per second, a number we've worked with a lot this year. We need to square it. So 1 times 3 times 10 to the 8 squared is just 3 times 10 to the 8 squared. So if you take 1 measly kilogram and convert it into energy, square the first part, 9, and 10 to the 8 when squared is 10 to the 8 plus 8, which is 16. You will get 9 times 10 to the 16 joules. That's an awful lot of energy from very little mass. That's the power of that c squared. All right, practicing a little further with our powers of 10 prefixes. Remember, the chart for those is on the front page of the reference table. Determine the amount of energy, or the amount of matter, in kilograms that must be converted to energy to yield 1.21 gigajoules. All right, what's a gigajoule? Well, we can't put gigajoules into E equals mc squared, so we have to look on the front page of the reference table to see what the prefixes for giga. If you do that, you will see that it's 10 to the 9. So we write E equals mc squared. And we want to solve for mass. So m equals E over c squared. And the 1.2 gigajoules has to go into our equation as 1.21 times 10 to the 9 joules over the speed of light squared, which will be 3 times 10 to the 8 meters per second. And then we have to square. Can't forget to do that squaring. When you do that, you will get 1.34 times 10 to the negative 8 kilograms. Not very much mass, but we're used to getting a lot of energy for very little mass at E equals mc squared. The key part is knowing that anything that's in front of the joules, you just can't put that into our equations. We have to go to the front page of the reference table and grab the proper exponent here to add to our 1.21. All right, one last item. In chemistry, you may have learned about atomic mass units. Well, here we're going to call them universal mass units. And you may have learned a universal mass unit or an atomic mass unit is 1/12 the mass of a carbon-12 atom. So really, it's just another measure of mass. And one universal mass unit is roughly 1.66 times 10 to the negative 27 kilograms. Now, typically in E equals mc squared type problems, the thing that's disappearing is going to be protons, neutrons, which are essentially universal mass units. So it might be helpful if we knew how much energy will you get if you destroy one of these items, basically a proton or a neutron. So it turns out that one universal mass unit, 1U, 1.66 times 10 to the negative 27 kilograms, whenever you destroy one universal mass unit, you get 931 mega electron volts, where the mega is the 10 to the 6. If you're looking at your prefixes of the powers of 10 on the front page of your reference table. Now, this is not something you need to memorize. This is on the front page of your reference table. On the list of physical constants on the front page, this is the fourth number up from the bottom. And in this course, whenever you see universal mass units, basically it's just going to be a conversion. So you're going to use your converting skills to go back and forth between U's and mega electron volts. So again, whenever you see U's or MEVs, it's typically going to be just a conversion. Let's try one. Convert 7 universal mass units to energy, because this is a unit of mass. So this whole conversion, somebody has done the E equals mc squared for you. That's how we turned this number into that number. So you don't have to do the E equals mc squared work because someone has already done it. Really, all you have to do is convert. So how do we convert? We do the factor label method. Oops. 7 U's. When you only have a numerator, we put it over 1. And then we need a bracket with our conversion factor in it. In order to get the U's to cancel, the U has to be on the bottom and the MEVs on the top. And then you could go to your reference table or look right up here and you will see that one universal mass unit is 931 mega electron volts. So you don't have to ask, do I multiply or do I divide? When you build the brackets, it shows you. So 7 times the 931 gets you 6517. And the U's cancel, and we're left with mega electron volts, or MeV. Again, whenever you see U's or MEVs, it's just going to be a conversion. And the 1U equals 931 MeVs is on the front page of the reference table. And Einstein's famous E equals mc squared equation is the third and final equation in the modern physics section of your reference table. So you could take a peek and see that below E equals HF and below E photon is E initial minus E final. There it is, the famous E equals MC squared.